Hello and welcome to this recorded e-learning on 7 Series DSP Resources. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the DSP Slice Resources, the pre-adder, and their applications. After completing this module, you'll be able to describe the primary usage models of the DSP Slice and describe the DSP Slice in the 7 Series FPGAs, its contents and its functionality. Now this recording is one of 3 parts. This first section here is going to discuss the DSP overview, and then we'll get into more of the details in the other recordings about the functionality of the DSP Slice. There's a growing performance gap between traditional DSP solutions and the performance required by today's increasingly complex DSP algorithms. With the DSP Slice's high performance and logic density, it's a significant solution to many applications, like you can see from this slide. In this case, what we're seeing is a lot of traditional processor architectures are running very good performance, but they can even run even better inside an FPGA, particularly when they're trying to target some of the newer functionality and new standards that are being used in DSP applications. One commonly seen DSP operation is a simple FIR filter. Shown here as an equation, you can see that a FIR filter is composed of the sum of many multiplication operations, with n representing the number of required multiplications or taps. Traditionally, a FIR filter is drawn as a set of n parallel multiplications with the results of all the multipliers feeding into a single adder to produce the result. This adder is usually implemented as an adder tree with optional pipeline stages to increase its performance. This implementation of the filter is the most straightforward. However, it is not the only possible implementation, as we're going to see in the next slide. On this slide, we see a side-by-side comparison of sequential versus parallel DSP processing. On the left, a DSP processor with only one multiplier and adder must loop through the data in coefficients n times, requiring n clock cycles to produce one accurate result. This process can be extremely slow depending on the number of multiply and accumulate operations required to produce the result. In this example, a 3960 tap filter running at 1.2 gigahertz can only process 303,000 samples per second, or KSPS. On the right, an FPGA with the appropriate number of DSP slices can perform all the multiplications in parallel, producing a result every clock cycle. The same 3960 tap filter can fit into the largest Vertex 7 XT device, which contains 3960 DSP slices. Although the maximum clock frequency is half the rate of the DSP processor, the increased efficiency of the parallel implementation means that the FPGA can process the filter at a rate of 600 million SPS. Although this diagram shows that all the multiplier outputs are feeding into a single adder, in reality there's a chain of pipeline adders that eventually produces the final result. The features of the 7 Series DSP Slice include input conditioning, pipelining registers, dedicated multiplier, an operational control, dedicated adder, and cascade paths, which are not shown in this diagram, for example, and are used to cascade products and sums to the neighboring DSP slice. Now, input conditioning includes the pre-adder and input pipeline registers. The pipeline registers, labeled here as Z1 and Z2 in the diagram, exist in several places within the DSP slice to maximize performance, just like any pipelined application. The multiplier and the adder are the main workhorse components of the DSP slice. Operation control registers and dedicated muxes allow different operations to be performed by a single programmable DSP slice, thus facilitating the programmability and the flexibility that is included with this DSP slice. Now, cascade paths are both for inputs and outputs, which are not shown in this diagram, and they allow multiple DSP slices to be chained together vertically to form wider and more complex functionality. Here's an example of how a FIR filter can be implemented using the DSP slice structure. This example shows a 4-tap filter. The input data is fed into the DSP slice on the left, where it is pipelined and cascaded to delay the data in time. The multipliers in each DSP slice multiply the data by the appropriate coefficient, and the adder outputs are pipelined and cascaded to form the final filter output on the far right. From this example, you can see how easy it would be to increase the number of taps in the filter. Simply add more DSP slices to the chain each with its own multiplier coefficient. Note that unlike building a DSP application with other resources, performance of this DSP slice application is not affected by the number of taps in the filter. This is because the cascade chain and the pipeline registers allow increased capacity at the same optimum speed. The flexible structure of the DSP slice makes it useful for implementing non-DSP functions as well. This example here shows how to adapt a basic adder tree to fit into the DSP slice architecture. The first step is to remove the pipelining from the adder outputs. This just simplifies the schematic to make it easier to manipulate. The pipelining registers don't serve any function other than to maximize performance, so it's safe to remove them. The second step is to redraw the adders so that they look like a chain. If you look closely, you'll see that the overall functionality has not changed. The same four signals are being added to form the output, just in a slightly different order. The last step is to reintroduce the pipeline registers to maximize performance. Because the adders are in a chain instead of a tree, every pipeline register in the adder chain requires a matching register in the data path. You should also notice that an additional adder has been placed at the front of the chain with one input tied to 0. Now it's easy to see how the adders and the pipeline registers will map into Xilinx DSP slices. Each blue box in this final diagram represents one DSP slice. Now this was a short introduction to the DSP functionality, so let's have a quick summary and then you can learn more about various applications and very advanced features in the next couple recordings. So the first thing we want to point out is that all 7 series FPGAs contain the same DSP48E1 cell. The DSP48E1 cell is identical to the one used in a Vertex 6 FPGA. It's commonly referred to as just a DSP slice. It has the following features: a 25 by 18 sign multiplier, a 48-bit add-subtract accumulator, that's a programmable functionality, so it can be either any of those, pipeline registers for high-speed pipelining, a pattern detector, SIMD operators, a cascade path that allows you to do very high fan-in functions and improve your system speed, a 25-bit pre-adder, and dynamic pipeline control. So far in the part 1 we looked at a DSP overview where we talked about some of the usage models as well as some of the needs for DSP slice functionality. Now we're going to get into the detailed contents of the DSP slice, and then in part 3 we'll talk about some of the more advanced features including the pre-adder, the dynamic pipeline control advantages, and finally IP support and the ability to infer the DSP resources from your synthesis tool. This diagram shows all the features of the DSP slice. The A, B, C, and D inputs enter on the left. The A and D inputs can be added or subtracted in the pre-adder, and the A and B inputs can be pipelined using the dynamic pipeline control feature. The C and the D inputs also have optional pipeline registers, and finally the A and the B inputs can be concatenated to form a single 48-bit input. The 25 by 18 signed multiplier takes the output from the pre-adder block and then multiplies it with the B input. In the center of the slice are 3 multiplexers labeled X, Y, and Z. The outputs of these muxes feed into the 48-bit ALU. The select inputs for all 3 muxes are controlled by the op mode register, which is located by the blue boxes at the bottom of the graphic. The ALU can perform addition, subtraction, or basic logic functions on the X, Y, and Z mux outputs. The ALU mode register determines the logic function being performed on the input data. At the top of these are the dedicated cascade paths for the A, B, carry out, and the product term signals going up each column of DSP slices. Finally, on the far right of the diagram, there's a pattern detector on the output which can compare the ALU result to either the output of the C pipeline register or a value set by the pattern attribute. When configured as an adder subtractor, the ALU operates on the X, Y, Z, and the carry-in operands. This table shows the ALU modes for addition and subtraction. The op mode register that drives the select lines to each mux can be updated dynamically to change the operands feeding into the ALU. The ALU mode can also be changed dynamically during operation. Now please note that when the multiplier is used, it generates 2 partial products, so both the X and the Y muxes are required to produce the final product. Now, before you get overwhelmed and start thinking that you're going to have to start manually programming or building each DSP slice manually, I want you to remember that most customers will use the core generator or the system generator to build their filter or other DSP components. Now, the system generator will build larger, more sophisticated DSP systems than are possible with the core generator. Now, these utilities allow you to easily build the custom component you want since they incorporate a GUI of selections for you to customize your core. Now, normally in an REL, we don't usually include questions, but in this case, we find it very worthwhile. So if you want, you can pause the recording or answer the question after I read it to you, but I think after hearing the question, you should at least try and read the answer in the notes and spend a couple minutes trying to determine how we came up with these operation modes. So let me explain to you first of all what the question is. So we have a circuit diagram up here of the DSP slice, and we see all the inputs, we see the adder, etc., and the pipeline of the product outputs. So given this op mode table on the right, which defines the behavior for the various inputs and the various values that can be assigned to them to build what you need to go through and understand how the selection, the programming of the actual ALU is defined, and understand how the X, Y, and the Z inputs will control how it's being used. So ask yourself this question. Simply put, how do I build the function to add the C value with the A and B value concatenated? And so what you would do is you simply scroll to the select list, and you can see the various bit patterns that have to be assigned to get an A and B concatenated, and then likewise to drive the C output. And from this, you can quickly see what the operation mode should be. Likewise, when you take the product of A and B and add to the C value, as well as you take the product carry in, add it to your carry, and then add it to your product to generate a new value. So take a few minutes and calculate those op modes and see if you can come up with the same answers that we got. Now, the dual pipeline registers on the B input are shown here along with the dynamically controlled pipeline feature. The clock enables on each register are not shown in this example. The decision to use the pipeline registers is made at the time of design construction using an attribute and cannot be changed after configuration. That is, they are literally bitstream controlled. Now, the green muxes indicate that the use of these registers is optional and is controlled by the bitstream. The final version of the B input is available to the X mux of the DSP slice and is also cascaded to the next slice up in the column. Depending on what you're doing, this might be useful to propagate that signal. Now, the yellow mux is dynamically controlled using a 4-bit in-mode input. This mux selects the output of one of the pipeline registers, whether it's B1 or B2, and feeds it into the multiplier, which is the B mult output. Now, here's the logic on the A and the D inputs of the DSP slice. The pipeline registers on the A input to the DSP slice are similar to those on the B input, as seen from the previous slide. Now, this includes the use of the dynamic pipeline control register. However, the output of the yellow mux feeds into the pre-adder as well. Now, the behavior of the yellow mux, the two AND gates, and the pre-adder is controlled by the in-mode input bits. Bit 0 determines which pipeline version of the A input is used. Bit 1 of in-mode drives either the A output of the mux or a 0 to the pre-adder. Bit 2 of in-mode drives either the D input or a 0 to the pre-adder at the bottom of the figure, and bit 3 of the in-mode determines whether the A output of the mux and the D input are added together or subtracted. Now, the ALU block inside the DSP slice can be used to perform two input logic functions as well as addition and subtraction. When used for logic functions, only the X and the Z mux outputs are used. The Y mux and the carry in are then ignored. This table lists the ALU modes for the different logic functions that are possible. The pattern detector on the output of the ALU can compare the ALU result to a constant set by the pattern attribute, or the C input to the slice. This feature supports symmetric and convergent rounding, saturation, as well as the use of terminal counts. The 48-bit ALU can also be broken down to implement multiple smaller functions. This capability is also known as a single instruction, multiple data, or SIMD. The use_SIMD attribute is used to configure the ALU as either a single 48-bit unit or two 24-bit units or four 12-bit units. The ALU mode inputs are shared by all of the small ALUs. Each small adder-subtractor even has its own carry-out output, which can be cascaded to the next DSP slice in the column. You should know, however, that when a DSP slice is used in a single instruction multiple data mode, the multiplier, however, cannot be used. The DSP slice also contains dedicated cascade paths that pass input and output data from each DSP slice to the slice above it in the same column. Cascade paths are available on the A and the B inputs, the product output, and the carry out from the ALU. The product output can optionally be shifted by 17 bits. These dedicated cascade paths enable wide functions and filters to be built using multiple DSP slices without negatively impacting performance. Now, the example shown here is a 35 by 25 bit multiplier built using two DSP slices. As you can see, the A bus is 25 bits wide and the B bus is broken into two slices. 18 bits go into the lower slice, that is the least significant bits, and 17 bits go into the upper slice. Note how the A bus is cascaded into the upper slice via the carry chain. Likewise, the least significant bit product, that's bit 17, is cascaded into the upper slice, that's the most significant slice, to build the most significant bit of the final product output. So let's wrap up this recording with a very brief summary. So in summary, we've seen some more of the details of the DSP48E1 slice, and we see that it's identical to the Vertex 6 FPGA's DSP slice. And we've seen the features including the 25 by 18 sign multiplier. It has a 48-bit adder, subtractor, and programmable accumulator. It has dedicated pipeline registers to improve the system speed, a pattern detector, the use of SIMD operators, cascade paths to propagate larger arithmetic functions, 25-bit preadder, as well as a dynamic pipeline control elements. Now we'll see in the next recording the use of the dynamic pipeline control elements. But before you go to that third recording, please take a second and give us your feedback on this recording. All you have to do is click on the icon at the end and submit an evaluation. And while you're at it, let us know if there's any other recordings you'd like to hear. Finally, I want to thank you for listening to this recording and learning on the 7 Series DSP Slice Resources Part 2. Again, my name is Frank Nelson. Thanks for your attention, thanks for your time, and thanks for your business. So now, as part of the third recording, we're going to move on from the DSP Slice contents and get into some of the applications, some of the more advanced features, including the preadder and dynamic pipeline control resources and how that gives you an advantage. And finally, we'll talk about IP support and how to infer the DSP resources. The DSP Slice contains a 25-bit preadder that can add or subtract the A and D slice inputs. This result can then feed the dedicated multiplier. This small change to the DSP Slice architecture provides a huge benefit for any operations that use symmetrical coefficients. By cutting the number of required multiplications in half, symmetric functions are twice as efficient and use half the number of DSP slices and use half the power. This diagram illustrates how symmetrical coefficients provide such a large benefit when using a DSP slice. With any filter, all the coefficients have to be factored into the calculations, but if the filter is symmetrical, then the calculation is faster and uses fewer resources. In this example, if the K13 and K17 coefficients are not identical, then the filter must contain 2 multipliers and 1 adder, which requires 2 DSP slices. But if the filter function is symmetrical, then K13 would equal K17, so we can use the pre-adder to add the 2 data samples together before they're multiplied by the coefficient. This can all be performed in a single DSP slice using the pre-adder. Here's an example of a 6-tap transposed filter built without using the pre-adder. From the diagram, you can see that the coefficients are symmetrical. That is, K0, K1, K2, then again K2, K1, and K0. Implementing this filter without a pre-adder, that is, in an older FPGA, would require 6 DSP slices, but of course, since it's symmetrical, it will require far fewer in the 7 series. Building the same filter using the pre-adder, you can see the savings that are realized. Using the pipeline registers and input cascading, the correct data samples are lined up and presented to each multiplier. Only 1 multiplier is required for each pair of the symmetric taps, so this 6-tap filter can be built using just 3 DSP slices. This thus uses half the DSP slices for the same functionality and speed. Another relatively new feature of the DSP slice is dynamic pipeline control on the A and the B registers. This feature allows a data sample to be read once and then used for more than one clock cycle. Now this feature is also included with the Vertex 6 as well as the 7 series of FPGAs. Here's an example of how dynamic pipeline control can be used to perform a complex multiplication in a single DSP slice. Multiplying two complex numbers requires 4 multiplications as shown in the equation. The 4 operands are read into the pipeline registers and clock enables are used to hold the data in the registers. The in-mode input is used to select the input combinations for the multiplier. Now the whole operation requires 4 clock cycles. On the first clock cycle, the real portions of the operands are loaded and multiplied. On the second clock cycle, the imaginary parts are loaded, multiplied, and then subtracted from the first result. At this point, the real part of the product is complete and read. Also, all of the operands are stored in the 4 pipeline registers. So now the clock enables are deasserted to hold the 4 values in the pipeline registers for the next 2 clock cycles. On the third and fourth clock cycles, the in-mode inputs are changed to present the appropriate inputs to the multiplier and to generate the imaginary part of the product. So a complex calculation was done in only 4 clock cycles for 18 bits of data and only needed a single DSP slice. All of this was facilitated by the ability to dynamically read the input mode inputs. The in-mode inputs would have to be built by the user, however. In this case, that could be done by a simple state machine to update the in-mode registers if necessary. Another example of using dynamic pipeline control is to perform a large multiplication using a single DSP slice. The DSP slice multiplier is 25 by 18, so to perform wider multiplications you have 2 choices. You can cascade multiple DSP slices to form a larger multiplier, or you can break the function down into smaller pieces and build a sequential multiplier as shown in this example. Now we're going to assume you can step through the equations seen here to see how the final product is assembled from all the partial products after 4 clock cycles. The key is to understand that every large multiplication can be broken down into 4 steps. In this case, a 42-bit number times a 34-bit number. When these numbers are broken down into A concatenated with little a and B concatenated with little b, where big A and big B are the most significant bits, you realize that this big multiplication can also be completed as 4 smaller multiplications. When these multiplications are broken down in this way, it only requires 4 clock cycles to complete the large multiply. Okay, now let's spend a little bit of time talking about the IP support for the DSP slice and how you infer the DSP slice resources. When customers write their HDL code, they should be aware that some basic functions like multiplications can be inferred by most synthesis tools, but for most DSP functions, the core generator tool will need to be used. New cores are released with each service pack of the ISE software of the core generator, and information on all cores is available by visiting the IP Center at support.xilinx.com. DSP slices can also be instantiated for use in highly customized or non-DSP functions. This example shows how to infer a simple DSP slice to multiply 2 values together. Note how the op mode is inferred based on the multiplication sign of the HDL code. The op mode is shown in the comment only as a reference to the user, so it doesn't actually trigger anything with the synthesis tool. Now, this code will work with XST, that's Xilinx's synthesis tool, as well as Synopsys synthesis tools. In this example, we see how inference of a simple multiply and accumulate function is easily done within your HDL code and is completely inferable within XST and Synopsys synthesis tools. This is an example of building a simple adder and then mapping it to the DSP slice resources. To have this inferred, the user will also have to use the use_DSP48 attribute within XST to get this targeted. Otherwise, XST will map this adder functionality to the CLB resources and you'll get a CLB implementation which will be less efficient and of course consume more power. Now, for more information about this attribute and other attributes, we want to encourage you to refer to the XST user guide to learn more about that. This is another creative example where a loadable MACC can be inferred by XST. Note that since neighboring DSP slices share a C input, then the adjacent DSP slices cannot use its C input. But just to remind you, only the simple stuff can be inferred by XST or Synopsys synthesis tools when targeting the DSP slice. Most designers would probably go right to the core generator to build their arithmetic functions and then instantiate that built component into their HDL code to get the targeted DSP resources. Likewise, they might also consider using the system generator to build their large DSP functionality and then instantiate that into their overall FPGA design. Okay, now let's wrap up this module and this series of recordings on the DSP resources with a short summary. So in summary, by now we've discussed all the contents of the DSP slice in some significant detail. We want to first remind you, of course, that there's several significant improvements that are beneficial in 7 series devices. So it's important you try and take full advantage of the dedicated resources included in the DSP slice for the 7 series. Now, all the features I've just described exist in both the 7 series, but are also included within the Vertex 6 and Spartan 6 DSP slice resources as well. So make sure you understand what you have and what you're using and how you're going to get it. So make sure you infer the resources you need for your adders, your accumulators, and that you use any necessary attribute to get those resources. And if you don't do that, then make sure you instantiate the component from the core generator. Now, there's some very useful resources available to you at support.xilinx.com. We first want to kind of highlight to you again the DSP Slice User Guide is extremely helpful, and as we also mentioned, looking at the XST User Guide for looking at coding techniques as well as special attributes that allow you to target the DSP Slice. So those are 2 very important documents to have a review of. Likewise, if you'd like to learn more about our course offerings, our RAL offerings, you can go to our webpage you see here below on the education site. But whatever you do, please take a second and give us some feedback on this RAL. All you do is click on the icon at the end of the recording and submit evaluation. And again, likewise, while you're at it, if you know another topic you'd like to learn about, please mention that as well. Finally, we appreciate your time and attention. Thanks for listening to this recorded learning on the 7 Series DSP Slice resources. This was part 3. Again, my name is Frank Nelson. Thanks for your time and attention, and thanks for your business.